The most important ones, if there's ideal conditions, they involve the three different kinds of things we've been talking about. Classical bits, qubits, and E-bits, the entangled bits. Maximum entangled state of 2 qubits. So these basic protocols involve these three kinds of resources: classical bit channels, qubit channels, and E-bits. The first one is the simplest. That's called entanglement distribution, and then we get successively more interesting and complicated. These are the building blocks for the later communication protocols, where you can study these and say, okay, what if we make one of the resources unideal? Like, what if we take the qubit channel and say, all right, maybe it's not ideal. What if we make it a noisy qubit channel? What happens? How much quantum information can we send? How much classical information can we send, etc. So what are the resources? The first is what we'll call a classical bit channel. Okay, and if you have a density operator that describes a qubit, it's just a 2x2 matrix. Has to be positive semi-definite with trace 1. What does a classical channel do? It removes the off-diagonal elements. It takes a quantum state to a classical state, right? This is classical with respect to some preferred basis, in this case, the standard basis. So if you send a qubit through a channel that randomly does nothing, the identity, or randomly applies sigma z, you work out the calculation, you see, oh, that eliminates the off-diagonal elements of the density matrix. Okay? So that's a classical channel. It only preserves the diagonal elements. The qubit channel, it just, you send the qubit through and nothing happens to it for an ideal qubit channel. Okay? And then we'll use this notation QQ to denote a perfect maximum entangled state. Okay? And then these are the basic protocols. So what is entanglement distribution? This is related to how do you prepare an entangled state in the first place, right? That are shared between two distant parties in distant laboratories. So what could you do? Alice locally could first prepare two quantum systems, 2 qubits, one in the state 0, the other in the state 0. Then she could apply this local Hadamard unitary operation, that's a kind of channel, a unitary channel, to one of her qubits. And then she could apply what's called controlled NOT gate. Okay, so why is it controlled NOT? The NOT is just this X right here. That's it flips 0 to 1 and 1 to 0. So it's like a classical digital logic NOT gate. Okay? The controlled NOT, it says if the first qubit is 0, don't do anything to the second qubit. If the first qubit is 1, flip the second qubit. Okay, so it's controlled NOT. What you do in the second qubit is controlled on what's there in the first qubit. Okay, so when you do these things, you can do the calculation and see that you evolve this product state to the maximum entangled state. Okay? So Alice could do these things locally. She could do the Hadamard, the controlled NOT. This is how we visually represent them in quantum circuit notation. And then what would she do? She would just send one qubit over a perfect, an ideal qubit channel. Okay, which might be hard to realize in practice, but suppose that you have it in principle. Then you get this shared entangled state. Okay, so then in a communication theoretic sense, we're trying to count up the resources that are consumed and generated in such a protocol. Right, so basically, whatever crosses the dotted line is some resource. Okay, so what did we do here? We consumed a qubit channel to generate a maximum entangled state. So that's what we write with this notation. That's entanglement distribution. Okay. So that's a very basic protocol. And that's what Michelle was asking about earlier. How do you make entangled states? This is one way of doing so, right? But then you have to figure out how to prepare these in the first place. So maybe if you have a good single photon generator that prepares a photon in a well-defined state of polarization, then you could make this 0 tensor 0. Okay. And then maybe by some quantum optical interaction, you could realize the C naught. Why am I talking about this? These are the Bell states. One thing you can prove is that if you take this matrix, the identity on one system, tensored with an arbitrary matrix on the other system, you sandwich that by the maximally entangled state, you do this calculation, it collapses to half, and then the trace of this operator M. Okay? So that's somehow a useful property. It's a mathematical property, but it's useful. And then when you look at, okay, if we make M the identity, then what do you get? You'll just get the trace of the identity is 2. So when you do this calculation, you get trace 1. And that's just the statement that phi is a unit vector, and if you overlap a unit vector with itself, you get 1. Right? The length of a unit vector is 1. But otherwise, if you use the Pauli matrices as this M, they're in fact traces. You compute the trace, they're 0 for each of the Pauli matrices. Okay? And you do this calculation for them, and then you see, oh, I get 0. So then what does that tell you? This set of states is an orthonormal basis for the state space of 2 qubits. Okay? So that's an important fact. And what does that mean? If we form the density operators corresponding to these vectors, they are orthogonal density operators. Okay? So then that means in principle they're distinguishable by some measurements. So then you see this and you start thinking, how can we use this? How can we put this to use in some kind of communication protocol? Well, what you can do is this superdense coding protocol. This is something that Charlie Bennett and Stephen Wiesner realized in 1992. And this was kind of the start of quantum information kind of thinking. Okay, so these states are orthogonal, right? That's what we were saying up here. If you multiply any of them, they'll work out to 0. So what does that mean? We said they're distinguishable. How are they distinguishable? By some measurement. Okay? So we can make a measurement channel that will distinguish these. Okay? That's called the Bell measurement. This is how we write it as a measurement channel. Previously we talked about measurement channels. This is a particular example. So you would send in your density operator that's in some kind of state, and then if you want to do a measurement with respect to this Bell basis, that's what it's called, the orthonormal basis we wrote on the previous slide, this is the measurement that you do. So then, if in fact the state were phi, you do this calculation, you get 1, and then you'd have 0, 0, and then all these other ones, the overlap is 0. So you'd just be left with 0, 0, and that's your measurement outcome. 2 bits, 0, 0. 2 classical bits. Okay. Similarly, if you were to prepare the state rho AB in this x phi, okay, and then you send it through the measurement channel, this right here, it would have overlap 0 with this one. You wouldn't observe that. It would have overlap 0 with these other 2, and it would have overlap 1 with this. You would have observed the outcome 0, 1. Okay? So that's the Bell measurement channel. You can do this by doing the opposite of what we used to make the Bell state, right? So to make the Bell state, we did Hadamard and C naught. If you do those, if you're trying to do the Bell measurement, you would do the C naught and then the Hadamard, and then you could do a measurement in the standard basis, like sigma z tensor sigma z. And then that would realize the Bell measurement. Okay. So now we can put all this together to realize a communication protocol. So this is what's called supernets coding. Before anything happens, we allow Alice and Bob to share this maximum entangled state. Okay, you just allow them to share it. How would they get it in the first place? Maybe you need to do this entanglement distribution, right? But we allow them to share this. And then they can use this entangled state as a resource for classical communication. So if Alice wants to send one of 4 messages, that can be encoded into 2 bits, 2 classical bits. So we'll call that x1 and x2. So if the bit x1 is 0, you do nothing. If it's 1, then you do the z, the Pauli z. Alice would do the Pauli z. Okay? And then similarly, if this x2 is 0, Alice would do nothing. If it's 1, Alice would apply sigma z. Okay? So that's 4 operations, and that's a local operation. On the previous slide, you see that if Alice does nothing, the state remains as phi. If she applies sigma x, you get this state. If she applies sigma z, you get this one, and then if she does both, you get this one. They're all orthogonal. So by a local operation, she can do this and send her share of the entanglement, her qubit, over an ideal qubit channel, send that to Bob. Bob can do the Bell measurement, and then can figure out which classical message she encoded. So that's supernets coding, and it's a famous and important protocol. And what does it tell you? Well, by using a qubit channel, see it crosses the dotted line, and by a maximum entangled state, which is also crossing the dotted line, they can generate, they can communicate 2 classical bits. Alice can communicate 2 classical bits to Bob. Okay. So why is that good? If they had 2 uses of an ideal qubit channel, then they could just Alice could send 2 classical bits to Bob, right? Because we can encode classical states into quantum states, and then they could send 2 classical bits that way. But this is somehow more economical, right? An entangled bit is cheaper than a qubit channel, right? A qubit channel can make an E-bit, but an E-bit alone cannot make a qubit channel. So it's cheaper than a qubit channel. So by using something cheaper, you can still send 2 classical bits. So that's why this is interesting in a resource theoretic sense. Okay? So that's supernets coding. Teleportation was discovered 1 year later. I think it was just the question, well, what it amounts to is Alice and Bob swapping what they're doing. Okay? So you sort of flip supernets coding around, and then you get teleportation. So instead of Alice doing the local Pauli operations, she'll do the Bell measurements. Okay? And Bob instead will do these local Pauli operations. Okay? But now it involves 3 qubits. Let me show you the diagram first, and then we'll go back to the math. So teleportation looks like this. What is the goal? You want to send a qubit to Bob. Previously we said, oh, just use an ideal qubit channel, right? That might be hard. It's hard to make ideal qubit channels, right? So what could you do instead? You could say, all right, well, we'll try to have them share this E-bit state. Okay, so we'll say, instead of allowing them a perfect qubit channel, suppose that somehow they share this E-bit state. And there are procedures to take noisy entangled states to these ideal ones. Okay, so suppose that by some mechanism they can share this perfect E-bit resource state. Then, by using that along with classical communication, you can realize a qubit channel. So that's why teleportation is interesting and useful. classical channel on its own cannot realize a quantum channel, right? A classical channel, you delete these off-diagonal matrix elements, right? An E-bit on its own cannot realize a qubit channel. But by using these weaker resources and combining them, you can realize the strongest communication resource of a qubit channel. Okay? So that's why this is interesting. So how does it work? Alice will do this Bell measurement, send the 2 classical bits to Bob, and then he'll do these rotations, these Pauli operations, conditioned on the measurement outcomes. And then you check the math and you see, oh, okay, the qubit's teleported. So the resource inequality is this one. By using 2 classical bits and using an E-bit, we can generate a qubit channel. How does it work mathematically? In some sense, it's like an algebraic trick. Okay? Suppose the state of your qubit is this alpha 0 plus beta 1. Right? That's what we talked about previously. The state is the density operator corresponding to this unit vector. Right? Then you work with the algebra of the tensor product. And you can prove an identity. You take an arbitrary psi tensored with the maximally entangled Bell state. And then you can rewrite the number that will go here will be 1/2. Okay? That's the proportionality constant. And then you have 4 terms in the superposition. Okay? So one of them is the phi on A prime and A. A prime is what you want to teleport, and A is Alice's share of the entanglement. Okay? And then the state that you wanted to send is actually there in the B system. Okay? But there are 3 other possibilities. So the 3 other possibilities is that you'll have this rotated Bell state along with a rotation of the qubit that you want to teleport. Okay? The state of the qubit that you want to teleport. Similarly over here, you'll have a sigma z rotation and zx and xz. That's what you get when you work it out. And so what does that mean? If Bob does the Bell measurement, this state, this vector here is orthogonal to this one, is orthogonal to this one, is orthogonal to this one. So when you do the measurement, you sort of break this superposition into 4 different possibilities, right? So you do the Bell measurement channel that we talked about previously, and then what you realize is a density matrix that's a probabilistic mixture of 4 different terms. Okay. The 4 different terms consist of the measurement outcomes, 0, 0 for the first one, and then tensor with psi here, right? And then similarly, this probabilistic mixture. So if then Alice reports the measurement outcome to Bob, if Bob learns it's 0, 0, he realizes, oh, I don't need to do anything, and then the state of my qubit is the one that Alice wanted to teleport. Okay? If it's 0, 1, then it's this, and then Bob knows, oh, I just do sigma x, and then I get the qubit that Alice wanted to send me. Similarly, if Bob receives the outcomes 1, 0, he can undo the sigma z, and if he gets 1, 1, he can undo the x and z. So what's very interesting is that this procedure here, it's universal in the sense that it works no matter what this input state is, right? The alpha and beta that represents the quantum information encoded in this input state, the procedure has nothing to do with the alpha and beta. So it's somehow universal or blind to the state that's coming in. Okay? When you do this measurement, it doesn't learn anything about the alpha and beta. The probabilities for the measurement outcomes have nothing to do with alpha and beta. They're just uniformly random. right? And then, of course, these operations that you do, they just depend on the classical bits, which in turn have no dependence on alpha and beta. So if I were to draw a box around this whole thing, then we could just say, oh, that's a qubit channel, right? That whole procedure realizes an ideal qubit channel. There are other things to say that are interesting. Before these classical bits reach Bob, his local density operator is a maximally mixed state. It's a uniformly random maximally mixed state. Okay? And so before these bits reach Bob, his state, when you average over these measurement outcomes that are not accessible to him, the state has nothing to do with the psi. Right? So that's where, like, if you were to trace out A and A prime, if you're doing the partial trace, you would be left with a mixture of psi, x psi, z psi, and xz psi. You can prove that that mixture is the identity matrix, the maximum mixed state. Okay. But when those bits are revealed, he learns what operation he has to do. Not necessarily anything about psi, but what operation he has to do to complete the teleportation. Okay. There was a famous teleportation experiment between two Canary Islands, and this is an actual picture of the experiment. The green laser is actually not the teleported photons. That was just to stabilize the equipment. The teleported photons were invisible and infrared. Okay. I forget what year that was done, but I think that might be a decade old. And now there are teleportation experiments being done between, satellite, and satellite to Earth. So, okay. 9:30. I think we should just go for like 10 more minutes and then stop. Also, in July, I suffered an Achilles tendon rupture injury, and this is the first time I've lectured for 3 hours, and it's hurting. So we'll just go for like 10 more minutes.
Actually, let's go now.
You have to go now. Okay, that's fine. Please take some time.
Okay.
Yes. Yeah. If you want to take tacos now, it's fine. I don't know what to talk about. This is a bit technical. It's a bit technical. Why don't we just talk about entropies and then we'll stop? Or do you have a preference? I mean, there are these other communication protocols, but let's just talk about entropies, then we'll stop. Okay. So this is some funny diagram. Old man reads in the newspaper. Sun is losing 600 million tons every second. Reads this. Maybe not newspaper, but science magazine. And then he's very concerned. Is it still there? He asks his wife. It's still there. She's like completely shocked, right? So you mouth open. And then how does it look? The same, right? So, even though the sun is, I guess the point of this is that this is somehow discomforting, right? So like, even though the sun is radiating and sort of losing all this entropy and information, it's so massive to begin with. It sort of has so much entropy to begin with that losing this much is not so much in the bigger picture of things. Okay. How do we measure uncertainty? I'm actually going to start with a measure called quantum relative entropy. Okay? So it's a way to compare two density operators, two quantum states. Maybe you want to characterize how close they are, how distinguishable they are. So you use this relative entropy. Okay? So rho can be a density operator, and sigma is some, you can allow it to be a density operator or some positive semi-definite matrix. Okay? And then you plug into this formula, which kind of looks like entropy if you've studied that before. If this term were not there, it would just be the negative of the von Neumann entropy. But this is relative entropy. Okay? And why is this important? Well, you can use it to build other entropy and information measures. Okay? And it's a measure of distinguishability. There's actually a physical meaning of this relative entropy in terms of what's called quantum hypothesis testing. It's an experiment which will tell you, it's a way that you're trying to distinguish rho from sigma if you have many independent copies of the state rho and sigma. If you have many quantum systems that are each prepared in the state rho or the state sigma, and then you're trying to figure out which state it was prepared in. Okay. So it's a measure of distinguishability with a physical and operational meaning, and one of its core properties is that it doesn't increase when you apply a quantum channel to both states. Right? So how do you interpret this? If this is a measure of how distinguishable rho is from sigma, if you then apply noise to both rho and sigma, then it's harder to tell them apart. They're not as distinguishable as they was before. So if you have a measure of if you have a measure of distinguishability, it should not increase under a quantum channel, a noisy quantum channel. Okay. So that's its core property, and then if you have this condition satisfied, it's non-negative. So in particular, if both rho and sigma are quantum states, the trace is 1 for both, and then you can prove that it's non-negative. Okay. And then the equality holds if and only if rho is equal to sigma. There's a measure of distinguishability that I skipped called trace distance, and this Pinsker inequality gives you a way to relate relative entropy to trace distance. Okay. The relative entropy can be considered as like a parent entropy, a mother of all entropies. And how do you get other entropies? Well, you can plug in particular choices for rho and sigma. We said we would allow sigma to be an arbitrary positive semi-definite operator. One such choice is the identity. If you plug in the identity and you work with the formula, and you put a minus sign in front, then you get the von Neumann quantum entropy, right, which we said generalizes the classical Shannon entropy. You can do this construction. You can plug in, if you have a bipartite state, rho AB, and you plug in identity on A tensored with the marginal density operator, what you get by tracing over A. If you plug that in, you get something called conditional entropy. I think I wrote, yeah, so conditional entropy, it can also be defined as the difference of a joint entropy with a marginal entropy. Okay. Another important measure is mutual information. So that's what you get when you plug in a bipartite density operator, and as the other choice, you plug in the tensor product of the marginals. Okay, so then it's like, how distinguishable is rho AB from a product state, right? And so if it's 0, if this evaluates to 0, then by what we wrote previously, rho AB must in fact be a product state. But if it's not a product state, this will be non-zero. You know, it'll be strictly non-zero, And so in that sense, the mutual information is a measure of correlation, right? It tells you how far you are from being a product state. There's another quantity called coherent information that comes up, and that's important in the context of quantum communication. So you can play with these different things. Another way to define mutual information is you could say, oh, it's the sum of the marginal entropies minus the joint entropy. That's how it's traditionally defined, but then when you write it this way, you see it's a correlation measure. Okay. So you can work with some math and then show that these two things are equivalent. Another measure is called conditional mutual information, and it's this particular linear combination of entropies. And it's applied to a tripartite quantum state, a three-party quantum state, Alice, Bob, Charlie. You can write it like this difference of conditional entropies also. Okay. So if we have the formula for quantum entropy, how do we evaluate it? Take a spectral decomposition of the density operator, right? That's something you can always do. And then, remember, entropy is given by this. This is the formula we're trying to evaluate, right? So how do you do it? Define this function, eta of x, negative x log x. So then the entropy is equivalent to this expression. And then this is something we skipped. It was in the previous slides, but if you apply a function to a matrix, you do this thing that's from functional analysis. And you say, oh, okay, that's just the function applied to the eigenvalues of the matrix, and then you do this kind of construction, and then that's the function of the matrix. So you apply the function to the eigenvalues, and then you do the sum with the eigenvectors, and that's the function applied to the matrix. That reasoning comes about from Taylor series approximations of functions, right? So if I had a matrix A, and then I wanted to apply a function to the matrix, if I take A times, if I want to get A squared, then it's just A multiplied twice, right? If I want A cubed, it's A multiplied 3 times. And then you can use Taylor series, and then you can prove that the way we define the function acting on a matrix is what you get from these Taylor series. Okay? So that's how it comes about. Okay, so continue with the evaluation. Now the trace, it's a linear operation. It commutes with the sum and the scalars. So then you just trace these individual projections, and the trace of those is 1. And then you get, oh, it's just the function of the eigenvalues. And that is the Shannon entropy of the probability distribution encoded along the diagram. Okay. You have a question? All right. You should feel free to ask. Okay. So what can you conclude from this? Suppose you have a pure state. A pure state is when one of the probabilities is 1 and all the others are 0. The entropy of a pure state, when you evaluate this formula, is just 0. Why is that? Well, if you know the pure state, then in principle, you could do some measurement to test for that pure state, right? So you could do a measurement, like suppose your state is psi, and you know that. Then you could apply a quantum measurement with 2 components, psi and identity minus psi. And when you do this measurement on that state, it'll return the outcome, yes, the state is psi with probability 1. And so in that sense, there's no uncertainty with the state when you do this measurement. Okay, so with pure states, that kind of thing is possible. With mixed states, no. Okay, so that's kind of a thing like you might wonder, okay, why is the entropy of a pure state 0? That's some kind of justification for it, right? Because even with pure states, there can be uncertainties in quantum measurements, right? There's the Heisenberg uncertainty principle. But if you do the right kind of measurement to identify the state, then there will be no uncertainty. Okay, so that's why that's the reason we think that it's reasonable that entropy is 0 for pure states. Let's talk about entanglement in entropy, and then I think maybe we should stop. Okay? Because there are interesting and funny things that happen with entropies of entangled states. So suppose that the psi is a pure state of Alice and Bob's systems. Maybe there's 2 qubits. There's the Schmidt decomposition that we talked about previously. So we know that this state can be represented this way. There are some probabilities. You take the square root, it's probability amplitudes, and then you have these orthonormal bases. So then, for this state, if you trace over B, the density operator, this is a calculation that we showed we didn't do before. If you do trace of this psi AB over B, the resulting state is this. X. Okay. This X is an orthonormal basis, and so that means that these probabilities are the eigenvalues, right? And then when you do that Shannon, you could do the same calculation if you trace over A instead, right? So here we traced over B. If you traced over A, it's like there's a symmetry in the calculation. You get the same eigenvalues, right? So for a pure state, the eigenvalues of the marginal states are equal. And what does that mean? By what we wrote in the previous slide, the entropies of the reduced states are equal if rho AB is a pure state. Okay. So that's an interesting consequence of the Schmidt decomposition theorem. And it's a useful observation and tool. One thing you can do, you can prove as an exercise that if you have a tripartite state, phi on A, B, and C, and then you do this calculation of the conditional entropies, it'll evaluate to 0, no matter what pure state you have. Okay. And then another kind of striking difference between classical and quantum is that conditional entropy can go negative. Okay. That's something that does not happen in classical information theory. It's always non-negative, but in quantum theory, it can go negative. And it's a signature of entanglement. Okay? So let's see an example of how that happens. Conditional entropy of the maximally entangled state, the even. The global state is pure, right? It's a pure rank 1 operator. So any rank 1 density operator is a pure state. Okay? So that's the case here. And so if the global state is pure, the entropy of the global state is 0. Okay? However, when you trace over the one of the qubits, the state is maximum mixed, which is the state of highest entropy. Okay? So what does that mean? The joint entropy is 0. You can have no uncertainty about the global state. The marginal entropy is 1. That's the highest value for a qubit, for the entropy, the maximum mixed state. So even though the global state can be completely, you can be completely sure about it and have 0 entropy, 0 uncertainty, the reduced state can be completely uncertain. Okay? That's a big difference between classical and quantum. And then when you do the conditional entropy calculation, it's this one minus this one, that's negative. That's in fact the smallest value of the conditional entropy for qubit for Alice and anything else for Bob. Okay. If the state's not entangled, then you can prove the conditional entropy is always non-negative. Okay, that's a calculation you can do. You need a tool called data processing, and then you can do it. It's not so bad. So what does this say? If the state's separable, the conditional entropy is non-negative. So suppose you plug in a bipartite density operator to the conditional entropy formula, and you get a negative number, right? What is the contrapositive of the statement? If the conditional entropy is negative, then the state is not separable, by definition entangled, right? Any state that's not separable is entangled. So the negative conditional entropy implies the state's entangled, and the negative conditional entropy is thus a signature of an entangled state.